Welcome to Khan Academy, and today we'll be discussing the topic of area under the curve. The first way and the easiest way is geometrically. So we're going to start off with a absolute value graph. So once you have that, you basically want to break it down into two separate triangles like so. And once you have that, you basically just take the area of both. So you got length of 5 and a height of 5. So that's area of 12 and a half. And that's the same for the other side. So plus another 12 and a half. So the area under the curve of the absolute value graph from -5 to 5 is 25. So another way to find the area under the curve other than geometrically is to write an integral for that function. So to begin, let's start off with just a cosine graph. Let's have our A point at 0 and B at, let's say, 5. So the general equation for an integral is area equals the integral of b and a, and then your function f of x, or in our case our cosine equation, and then followed up by d of x. And then the d of x is very important because that's like the closed bracket of that integral. So if we look at this example of this f of x graph, we're going to be looking a little bit about how the bounds work. So if you look at the bound from A to B, that would just be the area under the curve of this triangle right here, which would be 5 alone. And let's say you wanted to do it from A to C, you would just add up the area under the curve of this triangle and then this area here. So it'd just be 5, 7, 12, and then it'd be the same if you wanted to do it from the back end of the graph. So let's say you wanted to go from B to D, and you would just add 7 plus 6, 13. And that's basically the concept of your bounds.
Alright, and in this example we have our function here, and we want to evaluate it going from 0 to 2. Now we can check that over here on the graph using geometric patterns here. So we know it's 2 across, 4 up. 2 times 4 equals 8 divided by 2, because it's a triangle, would equal 4, and that would be that area. But if we want to evaluate that using integral terms, we would take the integral of this, which probably explained in a different person's video will lead us to somewhere here. That would be the integral of that. And we need to evaluate it, once again, from 2 to 0. Plugging in our values here, we would get 2 squared in there, minus 0 squared, which would equal 4 minus 0, which would get final answer of 4, which equals our area that we got geometrically. Our third and final way to get area under the curve is by approximation, specifically with Riemann sums. And right here we have our table with the function from the last problem of 2x going from 0 to 2. And here's the graph right here, and the area under this curve we found to be 4, and we're going to prove that or compare it to this approximation method. With left sums, we are going to take the difference in the x multiplied by the left y. So here it would be 1/2 times 0, 0, 1/2 times 1, 1/2, 1/2 times 2, 1, and 1/2 times 3, 1.5. Add that all together, we would get 3. Comparing that now with right sums, we would take the difference in the x multiplied by the right y, as shown here with a little l. So it would be 1/2 times 1, 1/2, 1/2 times 2, 1. And then it would be 1/2 times 3, 1.5. And then 1/2 times 4, which equals 2. And adding all that together, half times 1 plus 1.5 plus 2, that would equal 5. As we can see, these are not exact answers. 5 and 3 is different from the 4 we found geometrically and also using integrals, but this is just here to show you that there is a difference between the methods and just to compare them overall.